Section 2.7 Substitutions. So far, we learned several ways for solving differential equations. And in this section, we're going to look at some specific differential equations that didn't work no matter which method you use that we have learned so far. So far we learned separable differential equations where you separate the variables, homogeneous differential equations, exact, linear, Bernoulli, So these are the ones that we learned so far. But sometimes you come across a differential equation that none of these work. So what we do is there's a specific or special way of handling these kind of equations. And let me show you by starting with an example. If we have this differential equation, we are asked to solve it. So to solve such a differential equation, the first thing you can think about is if ln, the natural log, is not there, what happens? If natural log is not there, then it's possible to be solved using what we learned so far. But since ln is there, it makes the differential equation more difficult. But look at this trick, how this trick will make this equation easier. You can let u equal that extra or additional factor, which is ln of y. And this is, I'm substituting u equals natural log of y. Then du dx equals 1 over y times dy dx. So from that equation, that's dy dx plus y natural log of y equals y e to the x. So what I'm going to do from this equation here, I'm going to solve for dy dx, which is y du dx. So everything is going to be transformed from dy dx into du dx. This would give us y du dx plus y, this is u, equals, keep this the same. Now, just looking at this, one thing you can see that we can do is divide everything by y. You get du dx plus u equals e to the x. So I was able to transform everything from yx into ux. Now the new form looks easier, right? And to be able to solve this equation, we use the integrating factor, e raised to p of x dx, which is 1 here, e to the x. And we can multiply the entire equation x e to the x du dx. ex times ex is e to the 2x. Okay, so now this equation can be rewritten as d dx of e to the x times u equals e to the 2x. Then we integrate both sides. This one, the integral drops the derivative. This is e to the 2x and 1/2. If you use the u sub, u equals 2x, you get 1/2 e to the 2x plus a constant c. Divide everything by e to the x. This becomes e to the x ce to the negative x. But then remember, u is ln of y, or natural log of y, 1/2 e to the x plus ce to the negative x. You can leave it like this, or you can do e of that to find the y. I usually just leave it like that. Any questions about this? We'll go over one more example, but I want you to try it first on your own. Negative x squared e to the x. So solve this differential equation. So to solve this one, one idea would be to substitute u equals cosine y. Now du dx is negative sine y dy dx. So then the given equation becomes x. See, instead of sine y dy dx, we put a negative du. So negative du dx is negative sine y dy dx. So it's negative du dx plus u equals negative x squared ex. Notice everything is as a function in u and x now. Divide everything by negative x, we get du dx minus 1 over xu is x e to the x. Now we can use the integrating factor. Mu equals e the integral of negative 1 over x dx, e negative natural log of x, e natural log of x to the negative 1, x to the negative 1, or 1 over x. That's the integrating factor. Now we can multiply everything by 1 over x. Which is ex. Then we have d dx of 1 over x times u equals e to the x. Integrating both sides, ex plus c. Now multiply everything by x, so xex plus cx. But remember, u is cosine y, so cosine y equals x e to the x plus cx. You can leave it like that. Anyone has any questions about this? No questions?